Hello, hello everyone. Good afternoon, good morning, depending on your time zone. Thank you for joining us for this brief presentation on the analysis of a seismic catalog induced during an enhanced geothermal system, an EGS operation at the Collab project. So, this work is based on the results from microseismic monitoring. And what does microseismic monitoring do for understanding the behavior of geothermal systems during a stimulation? Well, it allows to get an image, basically, visualize the active fracture network, either newly induced or reactivated, within a developing or producing geothermal field. And the main outcome is in real time, having a real-time feedback, a real-time image of the processes caused by the hydraulic, chemical, thermal stimulation of the geothermal field. And this is done through the location of the events, of the induced events, and also getting the source parameters for them. And this can be interpreted in terms of fracture growth and the effectiveness of the hydraulic or chemical or any other type of stimulation. But also in post-processing, not only having real-time feedback is important, also in post-processing, microseismic monitoring and the investigation and the analysis of seismic catalogues yields a greater understanding of the treatment history and the fluid migration. Basically, analyzing the location and the parameters of the microseismic events, of the induced microseismic events, and how they cluster around during the treatment, allows us to identify hot zones and found areas of weakness where the fracture has been propagating, and understand how each of the treatment parameters match with the growth of our fractures. Right, so what is the main outcome? What's the main result from microseismic monitoring? Well, basically it's mapping. It gives us a map of the position, the growth, the position of events, the growth and the effectiveness of the hydraulic fracture in stimulation, basically to assess the completion objectives. Also allows us to get a map of the extraction and injection paths, match this with the treatment history, and get a picture of the path our fluid is migrating through. Putting all this together give us more information on the development of engineer geothermal systems, and enhances the understanding that we have of the long-term behavior of our reservoir. And by getting this understanding, we can manage and minimize seismic risk. This is the risk of inducing seismicity, undesired seismicity that might affect infrastructures on the surface and downhole, and also help us optimizing the productivity and recovery from the reservoir, and assist in the design and optimal location of production wells. So what are the main objectives of an enhanced geothermal system? Well, basically it's creating or enhancing a fracture network, and a fracture network that facilitates basically the maximum circulation of fluid between the boreholes so that the heat exchange is maximized. Also, of course, another objective is avoiding the interaction with in situ faults that can either induce seismicity, damaging seismicity, but also create paths for the migration of a fluid and the loss of the heat that has been exchanged in our injected water. So engineering the simulation of a suitable fracture network requires some careful planning, and typically this involves modeling fracture growth based on known local stress, the magnitude of this stress and the orientation of this local stress, knowing the rheology of our reservoir and the conductivity properties of our rock. And all this is summarized in getting a good understanding of our in situ discrete fracture network. However, of course, in nature we have heterogeneity everywhere. There are local stress shadows, rotation of the stress, and in fact, the fracturing process itself changes these conditions, changes both the heterogeneity in fracturing and also the stress, the local stress at points of injection. So, therefore, how can we validate our models? How can we actually get a picture of what's truly occurring during our stimulation? Well, this is where microseismic monitoring kicks in. It comes in to give us a picture of where the activity associated with this induced fracture locates and how it is, give us a full characteristics of our fracturing. And it's the basic essential feedback that we have for our enhanced geothermal system operations. Just basically giving us a picture of the propagation of our fractures. Okay, so what's the case study that we analyzed in this example, in this study, is the Collab experiment. It's not a commercial and an actual geothermal project, a geothermal application, but it simulates the conditions of typical EGS operations, allowing us a very well monitor, a fully controlled operation, so that gives us a way of understanding all the processes undergone by the injection of fluid, the stimulation of a fracture network, and allows us to extrapolate this to real commercial operations. And the objective is, of course, increase the understanding required for this EGS, the Enhanced Geothermal Systems, through a collaborative research environment to study the stimulation of crystalline rock at a very, very small scale. The scale of these fractures is in the tens of meters, and it's done at a depth of approximately 5,000 feet, which is roughly talking about almost 1,500 meters in depth. As I said, this is a heavily instrumented project, and the fracturing was monitored using an array of 12 hydrophones, 18 accelerometers, and 4 geophones. I mean, this is much higher than the instrumentation that we can get in real operations, but because we had access in this case to the vicinity of the injection well, it was possible to position all these different types of instruments around our stimulated fracture. Well, this resulted in the recording of almost 2,000 microseismic events or acoustic emission events through 2 different injection tests and the injection created to develop the notches in our injection borehole. So we can see here the seismic cloud, color-coded in this case by time. So cold colors will be the early events, and hot color, so red would be the late events induced during this test. And we can see that our fracture grew from the initiation points, ending up with a major fracture, which is colored here in red, roughly oriented northwest southeast. So what is the objective of this study? It's basically validating the application of microseismic monitoring for real-time feedback, and how can it inform us about the fracture network that's being induced. And we do this through the analysis of the microseismic catalog. A catalog is basically just a list of the events with all the full parameters, basically location and source parameters, magnitude, source radius, etc. Of them. And the idea is use this catalog, carry out some analysis, some statistical analysis on the catalog, and get us information, full information of our discrete fracture network. So, summary of the objectives is we want to characterize the induced and mobilized discrete fracture networks from the analysis of this seismic catalog. We want to obtain full characterization, that it's giving us the orientation of the fractures, the spacing and the persistence of these fractures, and also give us some information of the fracture connectivity, because this is some main outcome of this type of projects. We want to enhance the permeability of the reservoir, and therefore very valuable information is the connectivity in between these induced fractures. And this calculation has to be objective, that is not depending on the operator, if possible automated, and if possible perform in real time, so that we get feedback immediately after the recording of our seismicity. So, what sort of analysis can be done in real time on our results, or in post-processing analyzing a seismic catalog? A very basic one is looking at the spatial clustering of our events. And one interesting parameter is the degree of spatial non-randomness. That is, how far is our distribution from being a random distribution? Is there any pattern that can be identified in it? Is there any relationship in between our events? Do they cluster especially? And it's a very simple analysis, but it gives us an idea of whether there is some degree of relationship in between our events, which is basically the objective of any of these induced seismicity operations. The degree of spatial non-randomness is calculated like this, is giving us, it's comparing basically a random distribution of points within the same volume with the distribution of events that we have in that volume. The difference in between these two populations is the residual that we have here, and by normalizing that by the total number of pairs that we have in our catalog, in our seismic catalog, we come up with a number. And this number can be plotted for each interval that we are looking at. And if we have basically any degree of spatial clustering, our population and the random population will show a different distribution, and especially will differ at short separation distances. As we can see here, around a value of roughly around 5 or 6 meters of separation, we're getting a much higher degree of relationship, a much higher degree of clustering. That means, yeah, there is our events are not random, they are not occurring randomly in that volume, they are actually related to each other. There is a spatial relationship in between them. So, after observing this, we set our machine to identify these clusters, that it separates our cloud of events into independent spatial clusters. And a good way to do this is just using the k-means, which is a way of optimizing the separation of the events into clusters, and an objective way as well that machines can easily learn to work with and can easily apply. And we can see here, and we can probably look at that in three dimensions. You can see here that our events naturally split into 5 well-defined clusters, indicated here by by the color scale. Okay. Next analysis that it's performed once we have separated our events in spatial clusters, it's also looking at whether there is any correlation in between them, that it's temporal clustering, whether there is some relationship in between one event and the one occurring after it. And what would be the separation of events that are related to each other in time. So, and this is done analyzing the location pattern of sequential events. Sequential events are events occurring successively in between them in our catalog. So, an indication of some degree of correlation in between our events, some degree of interaction in between them, and what would be the interaction distance in between them, is looking at the curves of separation in between all event pairs, here in red, we can see that, and sequential events. We can see that plotted here in blue. And the distance where these two distributions cross can be interpreted as what would be the correlation distance, or the distance of interaction in between our events, where one event and another are actually related and likely interacting within each other. And if we think of this in terms of permeability, well, we could think that these two fractures that are recorded as seismic events are likely to be connected. In the case of this study, this distance is below 1 meter, and more detailed analysis yielded a result of around 60 to 70 centimeters apart. All right, so now we have split our events in clusters. We've let the machine identify the spatial clusters, and we've also come up with what would be the maximum or the observed interaction distance. So the next analysis that we can carry out to fully characterize our DFM is analyzing the structure of the what's the fabric of this mobilized DFM. And this is done by a very simple analysis, just analyzing the spatial distribution of events, fitting planes into every possible combination of 3 events within each cluster. So the machine has separated our events in clusters, and we analyze each cluster individually and look at the distribution of the orientation of these planes, and if there is a maximum identified, if there's a maximum preferential orientation, this is interpreted as the orientation of the fractures within each of these clusters. We can see here how the results of concentration of poles are interpreted. So concentration of poles in the center will be interpreted as mostly horizontal distribution of fractures, while on the sides, on the edges of our stereogram, will correspond to a mostly vertical, observed vertical fracture network. And because it's an statistical analysis and there's an oversampling of our events, this method is much less sensitive to any error in our location. And we simply analyze this, we carry out a sensitivity analysis. What will be the impact of our location error in identifying the structure of our fractures? And we can see here that even with a location uncertainty of 20%, will be at 20% of the size, total size of our identified plane. So a location error of up to 20% can still yield a result in what would be the dominant orientation of that plane. It will still be able to identify our fabric by this maxima in our plot of dominant orientation. So these are the results that we got, analyzing all events as a total and each of the individually identified clusters. And well, the results show that there is a clear dominant orientation for each of them. Cluster 3 was more random, no clear orientation found in it. But what was encouraging from this is that there was a match in between this and the observed macro fractures that were actually measured afterwards through injection tests. So yeah, there's the seismic catalog actually identified well the orientation of these macro fractures, and it corresponded basically to what would be our induced discrete fracture network. And we can see here the interpretation with for each of the clusters. So the overall dominating structure is a subvertical plane oriented along the maximum horizontal stress. So that's expected. But also we observed, and was also observed afterwards through direct observation in the boreholes, some shallow dipping structures that do not correspond, do not match what modeling would expect from the stress distribution. And the interpretation for this, that it could correspond to either the in situ fabric or some unmapped fracture, some unidentified fracture that created a weakness around those subhorizontal planes. So the orientations that do not correspond to these fabric or map fractures, well, need further investigation, because they could correspond to, they could be an effect of local stress rotations, or, as I said previously, an unmapped fracture, an unknown fracture that induced that other orientation. And well, what's encouraging is that this automated process match well with the observations, with the published observations from Schoenball et al. in 2009, direct observations of fracturing in this test. And well, this validates the approach as a tool for observation in real time of the nature and geometry of our fracture network. So, conclusion, well, basically, in this case, but also microseismic catalogues, allow us to characterize the induced or activated DFN fracture network. This information in real time can be used as a feedback to the engineers in the field, but also to update the models and estimate the effectiveness of the stimulation. and monitor the mobilization of critical in situ structures that could create undesired seismicity or undesired paths for the migration of our fluid. And as I said, this calculation can be automated for real-time monitoring of the impact of stimulation. So, thank you very much for your attention. If you have any questions, do not hesitate to contact us. Send us an email. And this video will be left in our YouTube channel for you to revisit. So, thank you very much. I'm looking forward to see you in our next webinar. Thank you.